Hello everyone, my name is Shannon Sweitzer. My colleague TK Satish Kumar and I are very happy you could attend our talk. Today I will be presenting our project on differential programming via OR methods. The presentation is going to have the following structure. First, I will present some motivation for this topic and some necessary background content. Then I will describe our methodology, along with an accompanying case study that illustrates how the method works. I will then present results for different classes of ODEs and systems of ODEs. Then I will extend this to an application to PDEs and describe how the method is adapted to handle multivariable equations. Towards the end of the presentation, I will describe how this method allows for the incorporation of inequalities. Finally, I will conclude with a brief summary and some future directions. With that said, let's get right into it. Let me begin with a little bit of motivation for this project. Ordinary and partial differential equations are the mathematical language of many sciences, including physics, biochemistry, control theory, and an abundance of other fields. Many analytical methods have been developed for solving ODEs and PDEs, including standard methods like separation of variables, integral transform, fundamental solutions, and so on. However, the applications of these techniques has been restricted to special classes of ODEs and PDEs, such as those with constant coefficients or equations of a particular degree. On the other hand, many numerical methods exist for solving ODEs and PDEs, such as the finite element, finite difference, and finite volume methods. While these methods are generally applicable, they do not return an analytical form, thus making their solutions unviable for downstream tasks. Furthermore, many domains require not only differential equations to describe their systems, but require the use of decision variables as well. Neither the existing analytical nor numerical methods can facilitate the search for the optimal values of the decision variables easily. These drawbacks motivate the need for a method that can accomplish several things. First, we would like to leverage the power of OR solvers and tools by casting differential operators in the language of OR. Next, we would like our method to produce an analytical form that is available for downstream tasks. We would like to be able to enforce desired properties on all points of the solution, rather than on a discrete set of points. Finally, we would like our method to easily be able to integrate decision variables and inequalities, thus making it adaptable to the needs of many different problems. In this paper, we present an approximate approach for solving systems of ODEs and/or PDEs using OR solvers such as CPX. The main idea is to represent entire functions as Bezier curves or surfaces with to-be-determined control points. The Bezier curves and surfaces have many nice mathematical properties, which we will discuss momentarily. In the following sections, I will present the success of our approach in several interesting classes of equations. These serve as a feasibility study of the effectiveness of recasting ODEs and PDEs, along with their boundary conditions, as constrained optimization problems on control points. Let me now introduce some terminology and notation. The Bernstein basis polynomials are defined by the equation given here, where n choose I is the standard binomial coefficient. The Weierstrass approximation theorem states that any continuous function on a closed interval can be uniformly approximated by polynomials. Bernstein polynomials are actually used in the constructive proof of this theorem. Here you can see an example of a continuous function with various Bernstein polynomial approximations converging to the function. Next, we have the definition for a k-dimensional Bezier curve of degree n, which in essence is a linear combination of Bernstein basis polynomials, where the k-dimensional coefficients p are called the control points of the Bezier curve. The curve is parametrized by t. Notice that the derivative of a Bezier curve is another Bezier curve with degree of 1 less, given by the equation here. Bezier curves have 3 key properties that make them particularly useful for an application such as this. First, they can uniformly approximate any continuous real-valued function defined on the interval 0, 1. This is established by the Weierstrass approximation theorem. Second, Bezier curves are closed under derivatives. That is, the derivative of a Bezier curve is a Bezier curve with degree 1 less than the original, and control points given by the relation you see here, where the pi's are the control points of the original curve, and the pi primes are the control points of the derivative. Third, a Bezier curve B of t is bounded by the convex hull of its control points, as shown in the figure here. Intuitively, this is because for any given value t in the closed interval 0, 1, the Bernstein basis polynomials are non-negative and sum to 1 when summed over I. Therefore, the Bezier curve B of t is interpretable as a non-negative linear combination of its control points, necessitating its presence in the convex hull. In particular, B of 0 is equal to the control point P sub 0, and B of 1 is equal to the control point P sub n. We can now elaborate on the details of the method of this project. The idea is to use Bezier curves along with their derivatives to approximate the function and derivatives of a differential equation. This reformulates the differential equation as a polynomial equation. In order to enforce this polynomial equality, we can form a convex optimization problem on the control points. Any initial and boundary conditions from the differential equation become linear constraints on the control points. In the next slides, we will illustrate this method through examples and case studies in order of increasing complexity and generality. Take the class of first-order homogeneous linear ODEs with constant coefficients. They are equations of the form here, and have the family of solutions also given on the slide. Consider, for example, the equation y prime plus 3y equals 0, along with the initial condition y evaluated at 0 is equal to 2, which belongs to this class of equations. If we represent y using a one-dimensional Bezier curve of degree n, and its n minus one dimensional derivative in for y prime, we now have an equation of a polynomial, let's call it g of t, equal to 0. The question is, can we find a set of control points p where this equation is true? The fundamental theorem of algebra provides the necessary method for finding the control points. The theorem states that a polynomial of degree n can have at most n distinct real roots. So, if we choose m at least n plus 1 test points from the closed interval 0, 1, and constrain the polynomial evaluated at these test points to be 0, the polynomial itself must be identically 0. Furthermore, the initial condition y of 0 equals 2 is reformulated as a linear constraint on the control points, namely that p sub 0 is equal to 2. However, n plus 1 constraints coming from g of t being identically 0 and the initial condition constraint create an over-constrained problem that in general will not be feasible. So instead of n plus 1 hard constraints, we can incorporate them into the objective function of a quadratic programming problem as soft constraints. You can see in the expression here on the slide that a squared error term is added to the objective function for each test point ti, I ranging from 1 to m. Minimizing a squared error penalty at least n plus 1 test points fully incentivizes enforcing the polynomial g to be 0. The resulting convex program can be solved using various convex solvers. We used CVX. The optimal values of the control points P0 through Pn can then be used to construct the Bezier curve B of t as an approximation for y. Here are some of the plotted results for homogeneous differential equations of this class. The Bezier curve solutions are plotted along with the known specific solutions, which we found via analytical methods, and you can see here that they completely coincide. This procedure was repeated for other classes of ODEs, including non-homogeneous linear equations. When the non-homogeneous term is itself a polynomial, for example 5t minus 3 in figure A, the problem again reduces to one of enforcing polynomial equivalence. However, when the non-homogeneous term is not polynomial, say something oscillatory like sine of t minus 3 in figure B here, the method can still be used since Bezier curves can uniformly approximate continuous functions. You can see in the two figures below the difference in approximation accuracy when the non-homogeneous term is polynomial versus non-polynomial. We also tested this approximation method on some higher order linear ODEs as well, specifically constant coefficient and Euler-Cauchy second order equations, since the solutions to these can easily be found analytically. Once again, the method performs best for homogeneous equations and equations with polynomial non-homogeneity terms, and performs well for non-polynomial non-homogeneity terms as the degree and number of test points increase. Our method can also be applied to systems of ODEs. In such cases, we must solve for a vector of unknown functions. We'll call it y bar of t. Consider the following system of linear ODEs with constant coefficients. The corresponding family of solutions depends on the types of eigenvalues of A, real or imaginary, but nonetheless the approximation method is the same. We can represent y bar of t using a Bezier curve with two-dimensional control points. We use the following quadratic programming problem with linear constraints to solve for the control points. For each test point ti, we add a term epsilon squared to the objective function. We also include m constraints of the form shown here in equation 6, which enforce the desired properties. The initial condition for this problem is formulated as b evaluated at 0 is constrained to be the column vector 1, 1. The next figure shows the solutions generated by the Bezier curve method. Again, the accuracy increases with increasing degree and number of control points, or test points. Since the motivation of this project comes from problems that often involve partial differential equations, we need to extend this to functions of several variables. The natural extension is from Bezier curves to Bezier surfaces, which are shaped by a matrix of control points rather than a vector of control points. For our illustrative purposes, we will focus on solving PDEs involving a function of two independent variables. The following is a k-dimensional Bezier surface of degrees n sub t and n sub u, which you can see is a Cartesian product of Bernstein basis polynomials in the semmend. Like with Bezier curves, Bezier surfaces can uniformly approximate surfaces with sufficient control points. They are also closed under partial differentiation. That is, the partial derivative of a Bezier surface is another Bezier surface, with control points given by the formulas below. They are also contained in the convex hull of their control points. Consider the following PDE with accompanying boundary condition. We can follow a similar method to that of the Bezier curves, that is, represent f with a Bezier surface of degrees n sub t and n sub u, and use its partial derivatives in place of the partial derivatives of f. We then have an equation of polynomial equivalence with to be determined control points, which we can find by implementing a similar quadratic programming problem, using a squared error objective function. For each test point, we add the term epsilon squared plus var epsilon squared, where epsilon and var epsilon come from the constraints given below. Unlike with the single variable case, where the boundary conditions were encoded as hard constraints, we now implement the boundary conditions as soft constraints since they involve entire domains. The test points were chosen from the domain 0,1 cross 0,1. The Bezier surface B with optimal control points found from the QPP on the previous slide is shown here, plotted against the analytical solution F. The two curves are an exact match. To demonstrate our method's effectiveness in the realm of physics, we also applied it to an instance of the 1D heat equation with Dirichlet boundary conditions, specifically the heat equation shown here. The resulting Bezier curve with optimal control points is shown here for varying degrees and number of control points. As with other cases, accuracy improves for increasing values of n and m. With the degrees n sub t and n sub u both set to 3, the approximation is not very good. However, by the time we reach n sub t and n sub u equal to 10, the approximation nearly coincides with the analytical solution, as seen in the figure C. Inequalities and differential operators are commonplace in robotics, physics, hybrid systems, and other areas of study. For example, a robot might have a maximum acceleration capability expressed as an inequality involving the second derivative of its motion profile. The Bezier curve method easily accommodates such inequalities since the framework is already that of a constrained convex program. Consider the following motion profile problem, where a robot is required to travel a distance L, starting and ending with 0 velocity. It has a non-negative maximum velocity, non-negative maximum acceleration, and a non-positive minimum acceleration. These constraints on velocity and acceleration all involve inequalities with derivatives of the motion profile L. The goal of the problem is to find the motion profile L and minimum capital T such that the robot travels the required distance and meets all of the requirements of the constraints. Using the Bezier curve formulation, which is a linear program with an outer loop of binary search for minimum T, we achieve the results shown in the figures here. The blue lines are the close approximations produced by our method, and the orange lines are the optimal velocity profiles derived from physical interpretation. Two different maximum velocities were considered in order to capture both the situation in which the robot does not reach maximum velocity and the one in which it does reach maximum velocity, plateaus there, and then decelerates. Both instances used 40 control points. To summarize, we have demonstrated the success of this Bezier curve method for several different classes of ODEs and PDEs. The main idea of the method was to cast differential operators in the language of OR so that we can leverage the power of OR solvers and tools. There are many anticipated benefits here, since many problems in science and engineering that may not be directly amenable to analytical methods can instead be solved programmatically using OR solvers. Powerful OR solvers are scalable to millions of variables and employ efficient parallelization techniques. This method has several key advantages, including the ability to reason with inequalities and decision variables, enforce desired properties on all points of a solution, and produce an analytical form for downstream reasoning tasks. Testing and verification of complex systems involving ODEs and PDEs can be done via highly scalable search-based methods instead of expensive simulation-based methods. Additionally, unlike with many numerical methods, the number of control points depends on the complexity of the approximated function, rather than the size of the domain. Some future research directions that we are interested in include representing local regions of a function with Bezier curves and stitching them together under continuity conditions. There are many avenues to explore in this topic. That concludes our presentation for today. Thank you very much for joining us.